The flow past a rotating cylinder is a fascinating flow feature. The effect of the cylinder rotation on associated circulation is to increase the velocity of the flow on one side of the cylinder and to decrease it on the other side. The ideal flow field around the rotating cylinder may be solved theoretically through the method of superposition of a doublet, a vortex, and a uniform flow. Considering the flow past the rotating cylinder, the velocity at the surface of the cylinder is necessarily tangent to the cylinder because the cylinder is a boundary, hence a streamline. The rotation of the cylinder induces an acceleration of the fluid beneath the cylinder and a deceleration of the fluid in the upper part of the cylinder. In turn, the Bernoulli equation implies that the pressure on the lower and upper wall of the wall must be respectively lower and greater than the static pressure. The resulting pressure force, a lift force, is directed downward, a negative thrust. The entire flow field may have two, one or no stagnation points on the surface of the cylinder, depending upon the relative strength of the circulation. For an ideal fluid flow, the drag force is 0, and the lift force per unit length of cylinder can be expressed analytically as shown here, where the negative sign indicates that the lift acts downward on the previous sketch for a positive rotation speed. The magnitude of the lift is directly proportional to the density of the fluid on the approach velocity, V0. This thrust is referred to as the Magnus effect. The Magnus effect is the reason that topspin tennis balls drop very sharply towards the ground. The topspin induces a lift force perpendicular to the ball direction, acting downward. More generally, the trajectory of golf, baseball, and ping-pong balls are affected by the ball rotation around its center of gravity, slice, or spin. Historically, the Magnus effect was investigated because of the drift of spinning objects such as musket balls, bullets, and ballistic missiles. The Magnus effect is named after a German scientist, Heinrich Gustav Magnus, who first described this effect in 1852. For real fluid flow, the lift and drag force per unit length of rotating cylinder may be expressed as shown here, in which CL and CD are dimensionless, lift coefficient and drag coefficient respectively. Experimental studies of the Magnus effect demonstrated that the ideal fluid flow theory predicts reasonably well the real fluid lift force. In this figure, the measured lift and drag coefficients are reported as a function of the ratio of the velocity at the surface of the cylinder, R omega, to the free stream velocity, V0. The Magnus effect is a classical illustration of ideal fluid flow theory applied to the flow past a rotating cylinder. It remains a fascinating flow pattern more than 170 years after its discovery. A basic understanding of the fluid dynamic process is critical in many real-world applications. They are discussed in a number of relevant YouTube video movies in the same playlist.